Hello everyone, Assalamualaikum warahmatullahi wabarakatuh and good day to every one of you. Welcome to my video. So in this video, we are going to learn on the topics on three-phase circuits. Okay, so this is my name, Dr. Nur Zulaili binti Muhammad, and here is my email address. So you can just feel free to email me whenever you have a question regarding the content of this video. Okay, so for the list of contents that we are going to cover in this video includes the following. First of all, we are going to see the generation of the three-phase voltage and currents. Okay, so we will see in details what is the three-phase voltage and currents and why do we need the generation and how to generate the three-phase voltage and also the current. And then next we are going to see the relationship between voltage and current in the three-phase circuits. Okay, so we are going to see what is the difference between the V line to line and also V phase, and also current line to line versus the current phase. Okay, and then next we are going to do the analysis of a balanced three-phase systems. Okay, in these subtopics we are going to do some calculation, and then we are going to see on how to do the analysis for a different topology of a balanced three-phase systems. Okay, and then the last subtopics, which is the one-line diagrams. What is the one-line diagrams and how we represent the three-phase systems into the one-line diagrams. Okay, so basically in this video we are going to cover only for the first subtopics, which is the generation of the three-phase voltage and currents, and then for the rest of the subtopic we will cover in the next following video. Okay, so now let's go to the first subtopics, which is generation of the three-phase voltage and currents. Okay, so some brief introduction on the three-phase systems. So basically the electrical power is generated, transmitted and also distributed in a three-phase systems. So for the three-phase system, it will consist of three-phase generators, three-phase of the transmission lines and also three-phase loads. AC power systems have a great advantage over DC system in that their voltage levels can be changed with the transformers. Okay, so meaning that in the three-phase power system, okay, so basically we are using the transformer in order to change the level of the voltage before we can transmit the electrical power. Okay, so the advantages of using the three-phase system over the single-phase AC power system is, first of all, the output power of the three-phase system is higher than the single-phase system. Okay, and then for the electric power transmission and distribution of the same amount of power, the requirement of the conductor material is less in the three-phase system compared if you are using the single-phase system. So because of the requirement of the conductor is less, so the three-phase system is considered as a more economical since we can get more power per kilogram of metal. Okay, the power delivered to the three-phase load is constant at all times instead of pulsing as it does in the single-phase system. Okay, so these three is the advantages of using the three-phase system over single-phase AC power system. So that's why in Malaysia especially, when we are going to transmit the electrical power from the generation side to the distribution, from the generation side to the customer, we are using the three-phase system rather than use the single-phase AC power system. Okay. Okay, next we go to the subtopics of generation of three-phase voltage and current. So the three-phase generator basically consists of 3 units of single-phase generators. Okay, meaning that you are going to combine the 3 different sets of a single-phase generator in order to make it become three-phase generator. So each of the single-phase generator is identical to each other, but it delivers power at a different times. Okay, when it's said to be identical, meaning that the magnitude of each of the single-phase generator is equal. Okay, when it's said that deliver power at a different times, meaning that each of the single-phase generator have a different phase angle from the others by 120 degree. Okay, meaning that the first generator will be starting at 0, and then the second single-phase generator will be starting at 120, and then the third generator will be starting at the 240 degree. Okay, So basically, this is the topology of the three-phase voltage source by using the Y-connected source. Here we call it as a Y-connected source. Okay, so you have 1, 2, and 3 single-phase generator combined together by using the Y-connected topology, and then now it becomes three-phase generator. Okay, so same goes to here. You also have a 3 different single-phase generator connected to each other by using a delta-connected topology. Okay, so this is also we call as a three-phase generator using the delta-connected topology. Here is the Y-connected topology. Alright. Okay, so let's consider the Y-connected voltage source as per this diagram. Okay, so now here you have a VAN, VBN, and also VCN. Okay, so basically the VAN represent the voltage between the line A to the neutral line. VBN represent the voltage from line B to the neutral line. And the VCN represent the voltage across the line C to the neutral line. Okay, so the VAN, VBN, and also VCN we call as a phase voltage. Okay. So if you refer to the diagram, so basically the signals here represent each of the VAN, VBN, and also VCN. Okay, so the amplitude of each of the signals have a same amplitude, and then the frequency of each of the signal are out of phase with each other by 120 degree. Okay, so you see the difference between the VAN and VBN is 120. Okay, and then the angle between VBN and VCN is 120 as well. So 240 minus 120 is 120. Okay, so if you have the voltage source that have a same amplitude, just like this, and then the frequency are out of phase with each other by 120, okay, just like this, so the voltage are said to be balanced. Okay, meaning that in this situation we have a balanced three-phase system. Okay, so for balanced condition, basically the VAN plus VBN plus VCN will be equal to 0. Okay, and then the amplitude of the VAN must be equal to the VBN and equal to the amplitude of the VCN. Alright. So the equation for each of the phase voltage is given by this equation, okay, where you have a VAN is equal to Vm sine omega t because it starts at 0. Okay, and then for the VBN is represented by Vm sine omega t minus 120. Okay, minus 120 because it start later. Okay, it start at the 120. And then VCN is equal to Vm sine omega t minus 240. Or you can also rewrite as a plus 120. Okay, where your Vm represent the peak voltage. Okay, so each of the phase voltage have a same peak value, so that's why you can just represent it by the same peak voltage. Okay, okay, so for the phase sequence, since the three phase voltage are out of phase with each other by 120, so there are two possible combinations of the phase sequence. Okay, so the first one will be this we call as a B, C phase sequence. Okay, meaning that VAN first, followed by VBN, and then followed by VCN. Okay, so for this one, we call it as a positive sequence. Okay, so it is known as a ABC sequence or positive sequence. In this case, the VAN leads the VBN by 120. This sequence is produced when the rotor rotates counterclockwise. Okay, so if you refer to here, this is the phasor diagram for the three-phase voltage with the ABC sequence, okay, where the VAN represent the V phase at the angle of 0. Okay, for VBN represent the V phase at the angle of negative 120. Okay, negative because it's lagging. Okay, lags the VAN. And then for the VCN will be lags later than VBN. So the VCN will be equal to the V phase and then the degree is negative 120 plus negative 120 equal to negative 240. Or you can also rewrite it as a V phase angle of positive 120. Okay, where the V phase is basically the RMS value of the phase voltage. Okay, and then the second combination is represented by this. Okay, where you see here VAN leads the VCN. Okay, so the VCN will be followed the VAN. So this one we call as a ACB sequence. Okay, A, C, and B. A first, followed by C, followed by B. Or we can also call it as a negative sequence. In this case, the VAN leads the VCN. Okay, so this sequence is produced when the rotor rotates in the clockwise direction. Okay, so for ABC, the rotor rotates counterclockwise, but for the ACB sequence, the rotor rotates in the clockwise direction. Okay, so for the VAN, if you refer to the phasor diagram of the ACB sequence, okay, for the VAN will be equal to the V phase angle of 0. Okay, same to here. And then for the VCN, okay, because VCN will be follow the VAN, so VCN will be equal to V phase angle of negative 120. Okay, for the VBN, okay, VBN here, VBN will be equal to the V phase angle of negative 120 plus negative 120 will be equal to negative 240. Or you can also rewrite it as a V phase positive 120 degree. Okay, where your V phase represent the RMS value of the phase voltage. Alright. Okay, so the phase sequence is actually can be defined as a time order in which the voltage pass through their respective maximum value. Okay, meaning that what comes first? Okay, maybe come with VA first, then VB, then only VC, or VA, VC, then only VB. Okay, so this phase sequence of a three-phase power plays a critical role in controlling the direction of rotation of the three-phase electrical motors, where if the rotation of the rotor is a counterclockwise, so meaning that it is for ABC sequence. Okay, if the rotation is a clockwise direction, so meaning that one is for ACB phase sequence. Okay, if this sequence is altered, then the direction of the motor will get altered as well and may cause temporary or permanent failure of the motor. Okay, so that's why we need to make sure the phase sequence does not change abruptly. Okay, so it is important to keep the phase in sequence or to maintain the proper phase sequence. Hence, for checking the phase sequence, there is a special device that we call as a phase sequence indicator or phase sequence checker for a three-phase supply. Okay, so this is very important. We need to check whether the phase sequence follow the correct order and then does not change abruptly, because once the phase sequence is altered, it may cause temporary or permanent failure to the motor itself. Alright, so that's all for now on the introduction on the generation of the three-phase system. And then thank you for your time. Thank you for watching my video. I'll see you in my next video. Okay, bye.